Good morning, ladies and gentlemen. Nobel laureates in physics and chemistry, laureates in economic sciences, your excellencies, members of the Academy, ladies and gentlemen. On behalf of the Royal Swedish Academy of Sciences, I wish you all welcome to the 2019 Nobel Lectures in Physics and Chemistry and the lecture of the Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel. Alfred Nobel wrote in his testament in 1895, 1 year before he passed away, that his international prizes in physics and chemistry should be used to reward discoveries, inventions, and improvements that have conferred the greatest benefit to humankind. Many of the Nobel Prizes over the years have been awarded for achievements that have provided not only concrete, practical benefits for us humans, but also another crucial feature, and that is knowledge. At the turn of the millennium, the Swedish public radio Science Studio asked 3 experienced science journalists to rank the 10 most important scientific discoveries or inventions during the previous millennium. They decided to put in the first place the scientific methods. That is, the approach to explore and investigate the world in a systematic way using objective methods. This is, of course, the common denominator of all great discoveries, as we shall hear repeatedly in today's Nobel lectures. Almost exactly 200 years ago, a 25-year-old chemist here in Stockholm was investigating a mineral collected from an island in the archipelago of Stockholm. The young researcher by the name of August Arvidsson realized after careful and extensive analyses that this mineral contained a component that did not fit with any known element. He concluded that it was a new element. It was given the name lithium by no one less than Arvidsson's teacher, Jacob Berzelius. He had just become the Secretary General of the Royal Swedish Academy of Sciences, and he would perform that task for the next 30 years. The young researcher, Arvidsson, was elected a member of the Academy a couple of years later at the age of 29. All of you have used one of Jacob Berzelius's many contributions to science because he was the one who introduced the very practical and useful abbreviations for the elements. O for oxygen, N for nitrogen, and Li for lithium, and so forth. How I wish that these accomplished chemists could be with us here today to hear about the incredible development in the practical use of lithium ions in batteries. Or, as the science writer Arthur C. Clarke phrased it in what has become known as Clarke's third law, any sufficiently advanced technology is indistinguishable from magic. Not to be mistaken, Arthur C. Clarke was a dedicated rationalist. The physics laureates will describe fundamental parts of our universe that tickle our minds with breathtaking possibilities. Planets outside our own solar system are now being described with different methods at an astounding rate. Not to speak of the thrilling challenge of dark matter and dark energy that we now know must exist. The scientific methods are beautifully illustrated also in this year's prize in economic sciences, where the 3 laureates have shown how important conclusions can be drawn by comparing different measures, different types of improvements, to see which ones are the most important and which ones are the most efficient to improve fundamental aspects of human life, such as health and education. So we have a fascinating series of lectures ahead of us. Knowledge will be served to us by the best experts possible. So I now invite my colleague in the Academy of Sciences, Professor Mats Larsson, who is the chairperson of the Nobel Committee for Physics, to introduce the laureates in physics. Once again, welcome everybody to this year's Nobel Lectures.
The focus of this year's Nobel Prize in Physics is the universe itself. This year's Nobel laureates in physics, James Peebles, Michel Mayor, and Didier Queloz, have taught us that we can understand the development of the universe in broad terms from its early years to the present days, 13.8 billion years later, and our place in the cosmos. The discovery and interpretation of the cosmic microwave background in the 1960s represents the birth of modern physical cosmology. Over the past 50 years, this radiation has been measured with increasingly sophisticated techniques and has provided the oldest and cleanest information about the early universe. But not only that, we also know that the cosmic microwave background played an important role in the formation of galaxies and stars. Theoretical discoveries in physical cosmology have all along been absolutely essential for our understanding of the development of the universe. Our first speaker is James Peebles. He was born in Winnipeg, Manitoba, in Canada in 1935. He studied undergraduate physics at the University of Manitoba and then in 1958 moved to Princeton University in New Jersey, United States, for a PhD with Robert Dicke as supervisor. He has remained at Princeton ever since, where he is now Albert Einstein Professor of Science Emeritus. Please join me in welcoming James Peebles to the stage to tell us about the development that led to this year's Nobel Prize.
Thank you, Professor Larson. I am deeply honored. Friends and colleagues, ladies and gentlemen, I am so honored to be here and so pleased to see so many of you to hear about pure curiosity-driven research. I began studying the nature of the universe on the largest scale on the advice of Bob Dicke. He was my thesis advisor, and I counted him after that as my professor of continuing education. The idea at those days was that the universe is uniform on large scales and expanding. I was deeply uneasy about the schematic nature of that theory and about the even weaker nature of the evidence that this is the way the universe really is. But I could see a few things to do. That led to a few more things to do, and that carried me through my entire career. Cosmology became a little more interesting with the discovery of a sea of radiation that nearly uniformly fills space, a temperature of a few degrees Kelvin. The story of how this radiation was identified is a complicated and I think a good illustration of, the way science operates. Bob Dicke gathered 3 of his junior members of his group. Oh, well, I have to remind you, the brief commercial interruption, that the story of how we got to this state in cosmology is recorded here in what is meant to be a scholarly history and also a personal journal of the voyage to the theory we have now that is so well established. So Bob Dicke is here with Dave Wilkinson and me. There was one other major actor, Peter Roll. He gathered us, the 3 of his junior members, and explained his thought that perhaps the universe expanded from a hot, dense state. He then suggested to Peter Roll and David Wilkinson that they build a radiometer to look for this radiation that would be left over from the early stages of the universe if the universe were hot. And he explained to me, you go think about the theoretical implications of finding this radiation or not finding it. We were perfectly aware that there may be nothing there to find, but we could see that it wouldn't take us long to learn that, and the technology of both the theory and the experiment was interesting. So I thought, and I think they thought too, we'll take a year or so and then we'll move on to something more interesting. We didn't move on to something more interesting because the radiation was discovered in a somewhat complicated way. In the late 1950s, Bell Telephone Laboratories was experimenting with communication by microwave radiation. That gave us these cell phones. Early on in this experiment, and here's an example of one of the antennas used, they discovered an anomaly. The engineers did a careful balance of the radiation produced in each element of the detector. They did the sums and found that to make the sums come out correctly, they had to ascribe 2 degrees or so of radiation coming into the antenna from the ground. They knew that was an entirely ad hoc fix because these antennae are wonderfully well designed to reject radiation coming from the ground. They had an anomaly. That remained what could be called a dirty little secret at the Bell Laboratories for 5 years. The anomaly was there, it was not understood, but the engineers had better things to do. In 1964, you notice the coincidence. 1964, the Princeton group started looking for this radiation. In that year, Arno Penzias and Bob Wilson determined to understand where this radiation was coming from. At the same time, of course, we have Peter Roll, who you perhaps can make out with the plaid shirt behind the radiometer, and David Wilkinson holding the screwdriver and looking very intelligent. At the same year, Penzias and Wilson are to be credited for the fact that they thoroughly investigated this instrument to find the radiation source. They could not find it, and they are to be credited particularly with complaining about it until someone heard and directed them to Bob Dickey, whose 2 junior members of his group were looking for what Penzias and Wilson had. I do remember when we learned that Penzias and Wilson may have what we were looking for, there was no sense of being scooped, no regret. It wasn't instead very exciting, because here is evidence that there's actually something there to measure and to analyze, something to employ both theory and experiment. Wonderful. I had been thinking about the implications of the experiment, of course. One possibility to consider very carefully is that the radiation is not there, that the universe is cold. If the universe is cold and expanding from a hot, dense state, then there is a distinct danger that the high pressure in the early universe would have forced electrons onto protons to produce neutrons. The neutrons can readily react with each other to form clumps, and there is a distinct danger that in a cold universe you will end up with no hydrogen, quite contrary to the fact that hydrogen is the most abundant element. So I thought of a way to get around that, postulate degenerate neutrinos. I tell you that because it's fascinating to consider that in the Soviet Union, Jacob Zeldovich, who was one of the designers of the Soviet nuclear weapons, had turned his attention to cosmology. He recognized that a hot universe would produce helium. He felt that there isn't much helium in old stars. He had the disadvantage of being in the Soviet Union where communications were strictly controlled. He didn't have a chance to learn, as I did, that helium is rather abundant. He then recognized that he would have to understand in a cold universe how we have a lot of hydrogen. He made the same postulate, degenerate neutrinos. It's an illustration of the fact that developments can occur apparently independently because the times are right. There is somehow an implicit communication among scientists that goes on occasion to lead us to advances. I did see that a hot universe would produce helium. We don't have to bother at all about that figure except to admire the beautiful curves and to understand that what it's saying is that in a hot Big Bang, you would naturally expect a lot of helium to be produced. You would expect some abundance of the other light isotope, deuterium. And it was at this point I learned that I had been reinventing the wheel, that George Gamow had earlier come across the same idea. Again, I'm struck with the fact that different groups can apparently independently come to the same idea. Here is one illustration of that. The end of the Second World War, great energy was released into arts and sciences. In particular, after the war, three remarkable individuals started thinking about the cosmology. Left to right, Bob Dickey. This is alphabetical. His photograph when he was an undergraduate at Princeton University, George Gamow, Fred Hoyle, and Jakob Zildovich. Of the three, George Gamow was by far the most brilliant intuitive physicist, the most brilliant I've ever met. But along with that intuition was a distinct lack of interest in following up ideas. In 1948, he laid out many of the basic ideas of our standard hot Big Bang cosmology, but he didn't pursue them. His ideas died away, had to be rediscovered. Fred Hoyle had brilliant ideas about a steady-state universe, but he so liked that idea, he had trouble letting it go. Bob Dickey and Jakob Zildovich each founded research groups. Zildovich's group faded away when the Soviet Union dissolved. Bob Dickey's group remains strong and active to this day. Here is an example of what came out of the thinking on my part about how the universe might evolve if it were a hot Big Bang. In the early universe, hot, that means that matter would be ionized. You would have a plasma. The free electrons scatter radiation. The thermal radiation in a hot universe would then couple to the matter and produce what is in effect a fluid with a little viscosity. Fluids, you know, vibrate. And any small departure from exact uniformity in the early universe would oscillate as an acoustic wave. That acoustic wave is suddenly decoupled when the temperature had dropped to the point that plasmas can combine to neutral matter. So you have a boundary condition. The oscillation stops. That means, as in a musical instrument, that you set a boundary condition that favors some wavelengths and disfavors others. Here you see an example of that on the left-hand side. A given wavelength is oscillating in amplitude as in an oboe. Then there is a stop, as in the end of the oboe. In this case, the decoupling of matter from radiation. Some wavelengths are favored, some disfavored. You produce a definite pattern in the distribution of matter and radiation as a result. Here is my first graduate student, Jerry Yu, in the middle with Bob Dickey and Dave Wilkinson. I worked out this theory of oscillations. Jerry Yu knew how to compute. He worked out the results, and we don't go there yet. We came up with a notion then of how a universe could evolve into its present structure with a distinct pattern in the distribution of matter and radiation. Before I continue with all that, let us go on to consider a problem that was to be discovered if the universe began hot, it is filled with a sea of thermal radiation. That thermal radiation would remain, but would cool as the universe expands. An important test, therefore, of this idea that we have a hot Big Bang would be to check that the radiation has a thermal spectrum you would expect from a universe that's homogeneous and not energetic enough to add much to the radiation present from the start. That demonstration that radiation is of a thermal spectrum took a long time because you had to get above the atmosphere to measure it. It's an interesting story that I cannot resist telling of how that was finally demonstrated. Two groups set out to make the critical measurements. What is the spectrum of that radiation, the intensity at each wavelength? And I have to get above the atmosphere to do it. Two groups. Here, do I have a pointer? Oh, never mind. You see John Mather in the back, the tallest person, Nobel Prize for the demonstration of the thermal spectrum of this radiation. Worth pointing out, tall at the back on our left, George Smoot. You see Ray Weiss, Nobel Prize, also Smoot Nobel Prize for detecting the small departures from uniformity of the radiation. Ray Weiss, Nobel Prize for detection of gravitational waves. This is an impressive group, and the others are of Nobel quantity too. Here's another group, University of British Columbia in Western Canada, Herb Gush, a brilliant experimentalist, and his two associates, Ed Wishnow and Mark Halpern. This is my favorite photograph of scientists at work. If you didn't know that these people had done something great, if you had only this image to judge them by, would it inspire confidence? Well, in fact, here are the results from the two measurements. The solid curve is a thermal spectrum, different scales, so they look a little different. The data points are marked. Either of them is Nobel quality work. The radiation has a thermal spectrum. John Mather, a prize for the top spot. Herb Gush, well, good luck. He came in a few months later. That's the way the game is played. During the time up till this demonstration, there were hints that the radiation is not thermal. That would mean that things are not simple, that the universe either began in a slightly inhomogeneous way, so we're seeing a mixture of temperatures, or that there were energetic events in the early universe that seriously added energy to the radiation. Either would tend to erase those pattern of oscillations that I just mentioned. During the time when there was a hint that there is not really a thermal spectrum, I disliked the thought of all that mess if there was an inhomogeneous universe or a lot of energy released. So I turned to the analysis of how the galaxies are distributed. There were catalogs then of galaxy distributions in the sky. They were begging for a statistical analysis, and so I took on the job. Here is Donald Shane on the left, yes, my left, and some graduate students. I decided to analyze Donald Shane's catalog of galaxy positions, and I've noticed a phenomenon. When something interesting is happening, graduate students will gather around. These people, all graduate students, plus Bernie Siebers, who wasn't in the photograph, gathered around to help me in analyzing these data, which are here. You see in this pile a copy of the handwritten notes in which Donald Shane, with collaborators, counted galaxies in small boxes in the sky, totaling 1 million galaxies. Took him 10 years. He didn't know what would become of those data. Nothing could be done with them. What do you do with a million numbers until you have high-speed computers? It was my distinct pleasure to, with these guys, produce a map of the galaxy distribution and show it to him, and to ask him, so Donald, is this what you saw? And he laughed and said, I was looking at this one galaxy at a time. The natural statistic to use to measure this distribution is endpoint correlation functions. Let's not get into any of the details. Let's just notice that you worry a lot in a catalog about systematic errors. Are parts of the sky poorly covered? Are other parts obscured by dust? Is there a pattern in this distribution that is not real, but rather an artifact of poor measurements? The way you check that is you use different catalogs that probe to different depths and look at whether this statistic scales in the right way so that it presents a consistent story of what you would expect if you were really measuring the intrinsic distribution of the galaxies. So, long story, happy ending. My colleague Ed Groth and I could see from this that yes, we had a good, reliable measure of the spatial distribution of the galaxies. A lot of work went into that. I collected it all in this book, the large-scale structure of the universe. You notice a publication date, 1980, that's almost 40 years ago. But yet, if you order a copy of this book from Princeton University Press, you will see a new symbol added. Now, in the early 1980s, a critical problem arose. We saw, as you've seen in that figure of the map of the galaxies are distributed in a very clumpy way. On the other hand, this radiation is remarkably smooth. In the early 1980s, we know that it didn't vary across the sky by more than a part in 10 to the fourth. How can you reconcile a clumpy distribution of galaxies with a smooth distribution of radiation? Surely, as matter grew together to grow the galaxies, they would disturb the radiation and make the radiation much more irregular than observed. It became, by 1980 or 1982, a critical problem. How do we understand this difference? I was forced to introduce a wild hypothesis to account for this. Imagine that most of the matter in the universe is not the stuff of which you and I are made. Give it a name. I didn't invent the name, others did. Give it a name, dark matter. That doesn't tell you anything about it, except that it is an hypothesis, it's a guess. This dark matter must only not interact with ordinary matter or with radiation. If it doesn't interact with radiation, then this dark matter may gather together into concentrations we call galaxies without disturbing the radiation very much. In fact, I computed that in this theory, the large-scale variation in the mass distribution would amount to 3 parts in 10 to the 6, 3 parts in a million. That was in 1982. 2003, we had last had measurements that could measure reliably the distribution of matter on large scales across the sky. The answer, 5 plus or minus 1 parts in 10 to the 6. Pretty close. Isn't it remarkable that I could write down a theory ad hoc and by pure dumb luck hit on a theory that works wonderfully well? I call it dumb luck because, in fact, when I introduced the notion of dark matter, it was taken up rather enthusiastically by the growing cosmology community. It made me very uneasy because I could think of other ways to account for that difference between the distributions of matter and radiation. This is just the simplest. Why should nature accept our notion of simplicity? Well, remarkably enough, it occasionally does, as here. Another remarkable fact that startles me to this day, I had to introduce, as I say, the notion of dark matter, something that doesn't interact with ordinary matter. Neutrinos don't interact at all much. They interact slightly, but it's really small interaction with ordinary matter. In 1977, a few years before I needed dark matter, particle theorists came up with the notion that there might be a new family of neutrinos with a high mass. These people, independently in 4 groups, came up with that notion in the space of 2 months. How in the world did that happen? As far as I can tell, they weren't talking to each other. It was just somehow a notion in the air. Furthermore, these people didn't know that astronomers were gathering a lot of evidence indicating that there is dark matter. I shouldn't say the word dark matter yet. There is subliminal matter around spiral galaxies. There was this evidence then pretty clear that there is subliminal matter, let's call it dark matter, around galaxies. They didn't know that. They had the notion that perhaps the universe will be expanding at escape velocity. That gave them a characteristic mass density, and they observed that this family of neutrinos could have that characteristic mass density for escape velocity. They didn't realize that they were offering a particle that would solve the problem of why the radiation distribution is so smooth. It's a curious property of the way science operates. The notion that we are expanding at escape velocity became very popular in the early 1980s and through the 1990s. for a simple enough reason. If the universe is expanding just at escape velocity, then whenever we came on the scene and decided we would like to measure the rate of expansion of the universe, we'd find the same answer. It's escape velocity. We didn't have to have come on the scene at a particular time. The evidence that was accumulating in the 1980s is that the expansion rate is slightly greater than escape velocity. If that's true, and it turns out to be true, then we have flourished at a special time as the expansion of the universe just started to become greater, appreciably greater than escape velocity. It's a curious fact that we have to live with, that we flourished at a special time in the evolution of the universe. It took a long time for people to accept that, and at that time I found myself playing a role of Cassandra, attending conferences and explaining to the people the evidence that I was collecting that the universe is expanding a little more rapidly than the elegant case of pure escape velocity. I remember a bright young colleague saying to me, "You're just doing this to annoy." And I had to admit that I did enjoy teasing them, but I meant it, and in time the community became to realize that in fact, this is the way it is. Here is some evidence, so I'm not going to get into it because life is short. Let us here notice the pattern. Here are statistical measures of the patterns of the distribution of radiation and galaxies. You notice it's wiggly. Remember the oboe. The favored wavelengths gives it a tone. Same physics here. The boundary condition now in time rather than in space prefers certain wavelengths, and here you see them illustrated. On the left, the distribution of galaxies. In the right, the distribution of radiation. Spectacular. The observations on the left are the distributions of galaxies relatively close to us. The observations on the right, the distribution of the radiation imprinted back when the universe was hot at a temperature of some several thousand degrees Kelvin, and the plasma was just combining to neutral matter. Yet the same theory with the same parameters fits both to gorgeous precision. I could go on with such images for quite a long time now. It's a really a great network of such tests that convince us that we have a theory that is pretty good. It is to be emphasized that our theory of the evolving universe is only an approximation, incomplete. We have this ridiculous dark matter put in by hand, yet needed, and so well following the observations that we're convinced is there, but we don't know what it is. We have then also Einstein's cosmological constant. When I began work in this field, all of the authorities assured me that the cosmological constant is got to be zero. It's just so ugly. That was Einstein's opinion. Wolfgang Pauli, Landau and Lifshitz, my textbook in cosmology. The cosmological constant is not there. It's there. We need it. It has a new name, but that doesn't help. It's still not, we still don't understand why it's there. So we have a theory that is wonderfully well established, but yet full of holes. What in the world is this dark matter? I just can't resist now saying that since we have we have a cosmology that is well established, a convincingly good approximation to what actually happened, lots of things to do in it, but it is such a simple story relative to the story, say, of elementary particle physics or condensed matter physics or chemistry, so complicated, that we draw some lessons that I offer on the way we do natural science. First, as was remarked, we operate on a postulate that nature operates by rules that we can discover. That's only a postulate. We have no guarantee that that's the way nature works, but of course we find that this postulate is very, very productive. The rules you discover sometimes are by pure thought. Pause to consider that Einstein introduced his theory of gravity, the general theory of relativity, just 100 years ago on the basis of very skimpy evidence. Yet that theory, now applied to the distribution of the expansion of the universe on large scales, passes deeply demanding tests. Pure thought led Einstein to an aspect of reality. It's a remarkable thing, but there it is. Sometimes we make advances by what I can only call a community feeling. Somehow the times are right. You can see an illustration of that in the decision following the Second World War and the release of energy in arts and sciences that these four people I mentioned independently, they didn't know about each other, decided that it's time to work on cosmology. Sometimes there's an unspoken feeling in the air. I am still so impressed by the way neutrinos were discovered. The idea of a fourth family of neutrinos that serve well as dark matter was independently introduced by four groups, and just a little before they were needed to help invent a good cosmology. And of course, on occasion, we're driven by the brutal weight of the evidence. I was driven to introduce dark matter because there was no easy way else to understand why the radiation is so smooth. Yet now we're very sure that the dark matter is there. And of course, we understand well, perhaps some of you have followed the science wars, the notion by some sociologists that our science is a social construction. Well, of course it is a social construction. Who else would have done it? But it is a social construction that is buttressed by an immense weight of evidence. Didn't I put down here some evidence, again, to remind you? No. Oh, there it is, yes. We have a theory of the evolution of the universe that is a social construction, but it is one that is wonderfully well tested and passes the test. At the same time, this theory has many open questions, and it means, therefore, that I'm very happy to be able to pass on to future generations a lot of interesting research problems that I have not been able to solve. I'll stop there. Thank you.